And okay, and we're going. So today we're going to talk about complex numbers. Don't let the name fool you, though. They're not. I don't think it's overly difficult. But complex numbers come from, and this is going to seem kind of silly too, this group of numbers that are called imaginary numbers. All right, it's kind of a stupid name. Because they're not technically imaginary. They are very real. But when they were first postulated, so when the first mathematicians were thinking about what are now called imaginary numbers, they weren't sure if they would actually be proven to be in existence or not. And so they kind of just called them imaginary numbers to start with and figured, okay, well, for now, I'm not sure, so we'll just call it imaginary so people can kind of understand what's going on. But then later on, it was proven that, oh yeah, these things are actually real things that exist and are used. And but then the name had been around for so long, because it took a really long time for them to prove that. And the name just stuck, because mathematicians had been calling them imaginary numbers for like 100 years. And so they were like, well, those are the imaginary ones. And so now, you guys get the joy of, as high school students, getting to call these things imaginary numbers even though they're not technically imaginary. So you get to be confused because they were lazy back a couple hundred years ago. But anyway, so that's what we're going to start with, though. We're going to talk about what is an imaginary number. An imaginary number actually, bless you, is generated from something that up to this point you have been told you can't do or is not true. But actually, in certain circumstances, it is. We just don't usually use it in the traditional sense. So an imaginary number basically is this. It's the square root of -1. Okay? Yeah, right? You've been told not your whole life, but for a little while now, you've been told you can't take a square root of a negative number. Well, that's kind of bupkis. You can. Maybe so. You can take a square root of a negative number. It's just so that you understand the math before where you are right now. We just say, okay, you can't do that, because there's no sense trying to explain imaginary numbers to an Algebra 1 student, because it's going to be a little above their head at that point. So we just say, okay, you know what? If it's negative, you just can't do it, so just don't worry about it. Okay, it just makes things easier at that point. But now you need to kind of readjust your thinking on the whole thing a little bit. But to keep it simple, what we do is we say, all right, so if the square root of -1 is kind of like our base number, instead of having to write the square root of -1 over and over again, we just call it I. Okay, so if you're working on a problem that ends up having a square root of a negative, we can write that in terms of this number I. Okay, but just remember that I is actually the square root of -1. Okay, yeah?
Negative, like the square root of -4 would be 4i.
It'd be 2i.
2i?
Yeah, so I was just about to talk about that, so think about it for a second. If you have the square root of -4, remember yesterday how we talked about simplifying square roots for just a little bit? Did I do that in this class? I think I just did that in 5th hour. No, I did that in here too. We talked about how you can break apart a square root, right? Okay, I said the back of the book is probably going to have them written that way in case you come across that or whatever. Well, that same kind of concept applies if you want to rewrite something like the square root of -4. So this one can be broken into the square root of -1 times the square root of 4. Does that make sense? Because -1 times 4 is -4. Okay, well, what's the square root of -1? I. And what's the square root of 4? 2. So this is I times 2, or the way we usually write it, put the I second, so 2i. All right, so then you can kind of see the pattern here a little bit. If you have a square root of something that is a perfect square but it's negative, like do this in one step for me. What's the square root of -81? 9i. Okay? Same kind of idea. So you can just jump right to the answer. But this is why that works, though. Okay? So one thing you're going to be asked to do is find the square roots of some of these square roots of negative numbers and just write them in terms of I. Okay? So let's just do one more just to make sure we got it here. So what about the square root of, like, negative 72? Now, what's different about this one compared to the other two that I just did? 72 does not have a square root. However, 72 can be simplified, though. Okay? So is there a perfect square that goes into 72 that I could pull out? 9? Okay. So 9 times 8? And do that way? Okay. So if I did the square root of, like, negative 9 times the square root of 8, let's say. We could break it apart that way. Well, what's the square root of negative 9? Careful. 3i, right? Just like the other ones. So this would be 3i, and then we still got the square root of 8 because we don't know the square root of 8. Okay, now this one, technically, you could keep going because there's still a perfect square number that goes into 8. 4 and 2. Okay, so we got one more step here. So we still got to have that 3i there, but then the square root of 4 times the square root of 2. So can anybody tell me what this final answer is going to be then?
Wouldn't it be 5i?
You're so close. You're close too. But... Okay, so what's 3i times 2? 6i. All right, you said 5i. You're adding them instead of multiplying them. So 6i times the square root of 2 would be that thing simplified. Okay, and again, it doesn't look simpler, but the smaller the number under the square root symbol, the more simple it's supposed to be. So that's technically what would be the simplified version of that thing. Okay. Now, there's a faster way to do this one, because if you guys are like getting annoyed that we had to do this process twice, and how do you know when you're done? Well, if you pick the largest perfect square that goes into 72, you only have to do it once. So let's try it one more time, and I'll show you. Anybody think of a larger perfect square that goes into 72? So we said 9 times 8 was a way to get to 72. What's another multiplication we could do and get to 72 where one of the two numbers is a bigger perfect square? Nope. 12's not a perfect square, and 18's not a perfect square. 36. Okay. 18 and 4 does work, but then you're only using 4, and then you'd have to end up using 9 again later. So that one still takes 2 steps. But 36 works. 36 is bigger than 9, right? So if we did the square root of negative 36 times the square root of 2, see how we can just do this in one step and we're done now? What's the square root of negative 36? 6i, and then square root 2. See how I got to the same spot? Just a lot faster. There's always a shortcut. There's always one quick way to get to the answer. It's just a matter of if you pick the right number to do it. The largest perfect square will do it for you. Okay? So, okay. So that's an imaginary number. Okay? Anything involving I that comes from a negative square root is going to be imaginary. Now, a complex number is basically a combination of an imaginary and what we call a real number. Okay? So, before we get into how a complex number comes together, let's just talk for a second the difference between real and imaginary. It's pretty straightforward. These two things are mutually exclusive. What that means is if you have some number, either it fits into one category or the other. Okay? So an imaginary number is anything involving I. So we would say that it's anything that looks like this, b times I, where b is just some number, okay? Something times I. If you notice, all of these up here that we worked on ended up something times I, where a real number would just be, well, the number without I, so call it a, okay? A complex number takes a real number and an imaginary number and adds them to each other, adds them together, okay? So it's got a little bit of both. A plus bi, right. So a complex number will always look like a plus bi. And so what we're going to do with complex numbers today is we're going to do operations with complex numbers. We're going to add them, we're going to subtract them, we're going to multiply them together, okay? And if you understand how to combine like terms and that sort of thing in algebra with x, this is going to be pretty easy. It's really the same deal, okay? Like, for example, if I was going to add a couple of complex numbers together, let's say like 2 plus 3i plus 4 minus 7i. You just add the real parts together and you add the imaginary parts together, just like doing like terms, okay? So, what would be my answer then if I added these two complex numbers together? Does that make sense to everybody? 2 plus 4 is 6. 3 plus negative 7 is negative 4. Done. Okay? It's just like terms. The i's go together. The constants go together. Done. All right. Subtraction. Same kind of thing. If we had like negative 1 minus I minus 3 minus 2i. Now subtraction, you just got to be careful about making sure that you keep all the negatives straight, but it's the same kind of deal, okay? So let's do the real parts. What would be the real part of that complex number when we're done? Negative what?
4.
Negative 4. Yep. Negative 1 minus 3, negative 4. Okay? The imaginary part. Nope. Nope. Just I. Got to keep that negative straight, okay? It's negative I minus negative 2i. That ends up being plus 2i, right? So negative I plus 2i, that's 1i, positive, right? So you have to distribute the negative into the other. So if it's easier for you, I've seen some people do this, where they'll take an equation like this, and then they'll go negative 1 minus I minus 3 plus 2i. They'll distribute the negative and then try to work it out, and it's easier to get to that if you do it that way. Okay? If you have trouble with your negatives in your head, and I fall prey to that all the time, just distribute it first, rewrite it. Takes an extra line, but whatever, and then you can do it that way. Okay. Now, the only thing that ends up being a little different is when we try to multiply these guys together. Okay? For the most part, it's the same. But because we're dealing with imaginary numbers, there's this interesting little twist at the end. All right, so let's try that one. So if we got the complex number 2 minus 5i, let's say, and then 1 plus 3i. All right, so again, think about algebra. Treat I like it's x again. What would you have to do to multiply these things together? We'd have to distribute, okay? And there's a special way of distributing when you had two binomials next to each other called FOILing it out, right? First, outside, inside, last. You just basically have to make sure that everything gets multiplied by everything, and then you add it all together, okay? So let's do that process real quick. So the f, first, 2 times 1, 2, the outside, 2 times 3i, 6i inside negative 5i times 1, so it's negative 5i. And then last, negative 5i times 3i, negative 15i squared. And then you combine all your like terms together, right? Okay, so we should have 2 plus I minus 15i squared. And most of us would say, good, got it, done. Okay? However, remember, I is equal to the square root of negative 1. If that's the case, what's I squared?
1.
Nope.
I.
Nope.
Negative 1.
Yep. Does that make sense? Take a look at it. I is the square root of negative 1. So if I'm going to do I squared, wouldn't I have to square both sides of that little equation then? If I square it, I got to square it. So what is the square root of negative 1 squared? Negative 1, right? It just cancels off the square root. So I squared is negative 1. Now that's really weird. This is another rule that we're breaking that we've talked about in the past. Anytime you square something, it's supposed to be what? Positive, right? Whether it's a positive or negative number, when you square it, you end up with something positive, unless it's an imaginary number. When you square an imaginary number, you get something negative. It would end up being positive 15. Yeah. So what we got to do here is we got to make a substitution. We got to take this and substitute it here in for I squared. Okay? Again, you wouldn't do this if it was x, because x is just x. But I is the square root of negative 1, so we can convert it back into a real number now if we square it. So we're going to end up with here 2 plus I minus 15 times negative 1. Because we know I squared is technically negative 1. Yeah, exactly. You got it. And there's kind of an interesting thing that happens here then. When you multiply two complex numbers together, your result is still a... Your answer, whether you're adding, subtracting, or multiplying complex numbers, the answer should be a complex number. That's how you can check. Okay? So when we did addition, there's the real part, there's the imaginary part, complex number. When we subtracted, there's the real part, there's the imaginary part, complex number. When we multiplied, there's the real part, there's the imaginary part, complex number. Should always be that way. Okay? So with the multiplying, you just have to be careful. When you're done doing all your foiling, the I squared needs to convert to negative 1 then, so that you can bring it back into what that complex number should be when you're all done with it. Okay? So that's doing the adding and subtracting and multiplying with that stuff. So then the only other thing that we're going to do with these guys then is see where they come about in mathematics. So if we talked about how people were talking about, like, they weren't sure if they existed and where exactly then would we be actually using these things. Well, we've been solving some quadratics, and it turns out, though, there are some quadratics before that we said had no solution, but if we consider imaginary or complex numbers in the mix, we can actually solve them then. Okay? So let's take a look at where that actually happens then, and what that looks like. So let's say I have the equation x squared plus 25 equals 0. All right, so just like yesterday, okay, one of those quadratics that we're trying to solve. So let's say I'm going to take a look at this and try to determine which one of those methods from yesterday would be the easiest for me to look at. Okay, I'm going to give you a hint. With this one, it's not going to be graphing, even though that's kind of the nice one to go to all the time because you can just do it on your calculator. Why why is graphing not going to work for this?
Because it wouldn't go on the x.
There would be no x-intercepts. This is x squared, which is a parabola that the vertex sits on 0, 0, and then it's been shifted. What direction, how far? Up 25. Are there any x-intercepts there? No. You're not going to see any solutions that are x-intercepts when you're dealing with imaginary numbers. They don't show up. You can't see them. So we can't go that route. So if that route's out, what would be the next best option, do you suppose? Try to do the square root thing. Yeah. We could factor. Factoring gets tricky with these, but we could do that. But the square root method is a little bit easier for this. Okay, so if we're going to do the square root method, what should I do next with it then? Okay. We want to isolate whatever's being squared, right? So we got to subtract that 25 over. And here's where we had the problem yesterday, right? If we ran into this, we said, oh, if I try to square root both sides, I can't square root negative 25, so there must be no solution then. But you can if you think about imaginary numbers. So if you square root both sides of this, we'd get x equals the square root of negative 25, which we know from today now is what? 5i. So the solution, actually plus or minus, right? I forgot about that. So it's plus or minus 5i. Okay, so there are still two solutions. Plus or minus 5i. So it's two imaginary numbers that are actually the solutions to this equation then. Okay, so that's one type of equation or a way that that would come about. Okay, so if you were to square both sides with that. All right, let's do one more. Let's see if they get... We'll do negative 1/2 x squared minus 4. Okay. So let's try the old square root method on this one too then. So tell me what I should do. All right, so add the 4. Okay, so divide by negative 1/2. How about instead of dividing by negative 1/2, what could I multiply it by? Negative 2, right? Anytime you have a fraction like that, I always want to think multiply instead of divide, because dividing by a fraction is just annoying. So you can multiply by the reciprocal, and it's the same thing. So if I multiply this entire equation by negative 2, okay, well, what's negative 2 times negative 1/2? Well, you're close. 1, right? So it's just 1x squared after I do that. So that's why this works, because that just becomes 1x squared, which is what we're going for. And then what's on the other side? Negative 8. Okay, so now we got kind of the setup that we want. X squared equals negative 8. So now we square root both sides again. So x equals plus or minus the square root of negative 8. However, what would that be as an imaginary number then? So you want to break this 8 into 4 times 2 is what I'm hearing. Okay, if you're going to do that, it's going to have to look like this then. Square root of negative 4 and square root of 2. Okay? You can't just pull the 4 out of a square root. It's still a square root. So we have to actually take that square root at some stage here. So what is the square root of negative 4? Careful. No. What have we been talking about today? 2i, right? Yeah, imaginary number. So x equals plus or minus 2i square root 2. So we just had to simplify that up. So there's the imaginary number. So maybe another way of writing this, I don't know if this make any more sense to you, but another way you could write this is plus or minus 2 square root 2 I. We just put the I at the end of it like that. I just reshuffled the deck there a little bit with those numbers and what order I did them. Then you can see that it's an imaginary number a little bit more clearly. 2 square root 2 is like the B part, and then it has I after that. So that works as well if you want to write it that way. But all right, so that's all I got. Any questions before I set you loose on the homework then? It's a lot of simplifying square roots and solving equations like we just did these last two. So, some, but you got some time.